This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
We are the paradoxical ape. Bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves. Aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. CARTA brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
Life takes energy, and nowhere is that more keenly felt than in a population like the Hadza, who I'll talk about today. The Hadza are hunter-gatherers who live in northern Tanzania, and they're about 12 hours ahead. So right around now, they're starting to stir, maybe thinking about waking up, and by the time we're all sitting around over cocktails talking about all the great talks, they'll be waking up and figuring out how it is they're going to feed themselves that day. And every day they're out hunting and gathering and getting honey and all these other foods that they know how to get from their landscape. But it's a serious matter because all of life's processes, all the obvious ones like walking and running, but all the unobvious ones like immune function, nervous system function, growth, reproduction, somatic maintenance so we can live a long time, all those things take energy. And so we as any organism does, are forced to figure out how to fuel all of our daily activities and daily functions. Now, Darwin's great insight was that life is a game of turning energy into kids. The point of life is to reproduce. It's one of society's great ironies that has been picked up as a political platform by people who don't like Darwin very much. But that's another topic. But because of the sort of centrality of energy and energy expenditure to biology and evolution, when I look at the origin of Homo, or put humans in a broader context across our larger evolutionary family of the other apes, what I see as someone who studies energy expenditure and physiology from an evolutionary perspective, I see a story of energy expenditure and energy metabolic strategies changing. So one of the big obvious ones, if we look through the fossil record and we can track some of these changes, one of the first things we would notice is that right around 2 million years ago is when we start to see a big increase in brain size, as has been talked about already. Our brains are so big at this point that they consume about a quarter of our energy while we're sitting there resting. So every fourth breath you take is just the oxygen to fuel your brain as you're listening to me talk. Other things show up too, and so we see a change in diet. So it's a change in the way that we're getting energy. Bigger bodies, perhaps. I published a paper in 2012 that reviewed data on body size and suggested that body size does get bigger. So that's my scarlet letter, even though, as Carl pointed out, people suggested maybe they don't get bigger right away. Oh well. Anyway, the point about science is to be wrong, I guess. We know they're getting more active. They're ranging further. Dan Lieberman talked a lot about this endurance athlete phenotype that evolves with early Homo and is obviously going to be costly. As Leslie just talked about, we have life history changes that happen at least piecemeal and perhaps as long ago as 2 million. Maybe some of them don't happen until later, but that's a big energy expenditure change. Humans are the bunny rabbits of the ape world. We reproduce really quickly. So that was, whenever that happened, that's an expensive change. And of course, things like fire and cooking also change, as Richard Wrangham has pointed out, the way that we get energy and the way that we use it. And so all of the things that we think about as being sort of the human adaptive suite, the thing that separates us from other animals, these big ticket items here, all come around with the origin of the genus Homo in the last 2 million years, and they almost all, in fact all of these issues, including some of the others mentioned today, they all revolve around or touch on energy expenditure and the way that our bodies sort of budget and spend and allocate the calories that we use every day. So that's all well and good, but when you start kind of doing the math on the back of the envelope, you find out that this adaptive suite that we've got causes a real accounting problem, okay? In mammalogy, when we look across species, we generally see that if a species has a really big brain, then it has a smaller gut. Or if it has a really expensive, if it reproduces at really high rates, it has a shorter lifespan. And that's because, in general, across mammals, you can't get something without giving something else up. Trade-offs are the norm in all of biology and in mammalogy especially. But when we compare humans to the other apes, what we see are not trade-offs. We see that we are having, again and again, in terms of brain size, day range, how far you go every day, how long we live, how many and how big our kids are. We see again and again that we have exceeded the other apes in all of these really costly traits. So the human adaptive suite is really expensive. And it isn't clear at all how it is that we can afford to have evolved it. And if we can't explain the how, then we're going to have a very hard time explaining the why. So with that in mind, and knowing, as Dan pointed out, that all of these traits evolve in the context of hunting and gathering, my colleagues Dave Reichland and Brian Wood and I decided to see if we could make some headway on this by measuring daily energy expenditures in hunter-gatherers, those Hadza hunter-gatherers that I mentioned before. The idea there was we have these really expensive things happening. They're important in understanding our evolution. And we thought, as all of you, I would wager, think, that lifestyle, ecological context is really, really important for how many calories we spend. If we have a really active lifestyle, we expect to burn more calories. And so we wanted to know how many calories are spent every day by Hadza hunter-gatherers who still have that hunting and gathering lifestyle in which these things evolved. Would we make any headway by looking to see if we could make sense of the accounting, the caloric accounting, by measuring energy expenditure there? And that's where things got weird. So how do we fuel this? Well, just because not everyone here is going to be very familiar with a Hadza, again, they're a traditional hunting and gathering population. They're sort of textbook. In fact, they are the hunter-gatherers in your textbooks. Men hunt, women gather, men also collect honey. They live without domesticated crops, without domesticated animals and machines. Women work very hard every day, walk 6 kilometers a day, often with a kid on their back, and when they're not walking, they're working. So it's a physically demanding lifestyle for women and for men as well. Men are out walking often 12, 15 kilometers. It isn't uncommon for them to go 30 kilometers in a day to track down game. And they also climb trees to get honey. It's a physically hard lifestyle. And again, the whole reason that we spent 3 years getting funding and permits and going to do it was that we knew that these guys would be burning calories like crazy. And we wanted to understand just how much that cost so that we could get a sense of what hunting and gathering lifestyles looked like in terms of calorie expenditure. And so what we did was we went and lived with the hunter-gatherers, Hadza hunter-gatherers for a couple of months. Again, Dave Reichland and Brian Wood, I want to make sure I acknowledge, without those guys, we wouldn't have been able to do this, especially Brian, who's been working with the Hadza for years. And we measured daily energy expenditure with a method that you might not have heard of. It's called the doubly labeled water method. And what it does is rather than estimating your energy expenditure based on your activity, it measures your energy expenditure by tracking isotope flow through your body. You drink some isotopes, and then we watch those flush out over the course of a couple weeks. And it actually lets us track how much carbon dioxide your body makes. And that gives us a very precise physiological measure of how many calories you're burning. Totally safe and non-invasive. We do this in Western contexts all the time. But it's it is the way to measure calorie expenditure in sort of daily normal life. And here's what we found. So here is fat-free mass, lean mass, against daily energy expenditure, calories per day. And there we have your US and European adults. Open symbols are women and closed are men. So this is us. This is this room of people. Okay? And bigger people burn some more calories than smaller people. That's what that trend is telling you. And again, we knew when we looked at the Hadza, what we'd see is they had jumped off of this cloud really high and had hugely expensive daily lifestyles. And we didn't find that at all. These are the most surprising negative results I think I've ever gotten. It was really strange, and we didn't have a great explanation for how, but we knew the data were sound. And so that got me thinking about origins of Homo, the way we think about energy expenditure evolving. What's going on here? The old models don't work. We need to think about what does. So there's no difference between energy expenditure and Hadza and Western lifestyles. Along with this, I started doing a series of energy expenditure measurements, same technique, across a big range of primates, including a lot of apes, a lot of other species. And here's what those data look like. Here's body mass versus daily energy expenditure. The primates are on that red line. And you see they're shifted low compared to the non-primates. Now, this is a log-log graph. It doesn't go 1, 2, 3. It goes 1, 10, 100, 1,000. And on log-log space, you hide a lot of variation. What that grade shift means, even though it doesn't look like much, is that primates only burn half the calories that we'd expect for a mammal our size. In other words, evolution is pushing metabolic rates around wildly. Primates are just as active as other animals are, but they're burning half the calories. That's crazy, right? Our models for how we think about energy expenditure working are wrong. Even weirder, primates in captivity in the zoo burn exactly as many calories as primates in the wild, right? Your ideas about, and my ideas too for that matter, about how energy expenditure works don't work. Why not? Well, it turns out that we've all been lied to. Okay, so just the take home here is that, again, we see big evolutionary changes in energy expenditure. Lifestyle seems to have no effect. Why? Well, here's why. I'm going to show you data from a study where they took a bunch of people and trained them to run a marathon. They took people who were not active at all and trained them to run a marathon. And every couple of months, because they did this over the course of a year, as they're increasing how much they're running, that's the x-axis, they would check in and ask how many calories they're burning. And you would expect, as they go more and more and more and more running, right, that it would just go up, 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 up with energy expenditure. Instead, that's what happens. Okay? The gray line is the expectation. The black line's what really happens. We just published a study that is a snapshot across a big survey of people with different lifestyle activity levels, and we see the same thing cross-sectionally. That physical activity level doesn't have a huge effect on energy expenditure because the body is defending an energy expenditure throughput in the same way, kind of, that you defend a body temperature, right? No matter if it's cold or hot outside, if you're working hard or not, your body wants to be at 98 degrees. No matter how much you've eaten or whatever, your body's trying to keep your blood glucose levels in the same place. This is homeostasis. This is a trait that your body is trying to hold on to and defend. Well, that's really cool. What that means is that we can look at daily energy expenditures as an evolved trait. Okay? Now, on the flip side, it means that we can't fix the human energy paradox by just shoving more energy in, right? It's not like the wood chipper in Fargo, right? You can't just keep on pushing things down. There's a limit. There's a limit, right? This is the limit that gets defended. So models of human evolution of Homo that involve getting more energy from the environment and bringing them in, those are all well and good, and we need that. We need more energy to come in, but that's not sufficient. We also need to evolve a metabolism that will be able to use it. We need to evolve a bigger wood chipper. So then the question becomes, if that's the human energy throughput, How does it compare to the other apes? Does this give us a way out of the human energy paradox? Perhaps we've cranked up the volume on our metabolism, and that allows us to fund and fuel big brains, big activity, fast reproduction, long lifestyles. So we can go back to this data, and we can ask, relative to the trend line for primates there, where do humans fall out? Are humans high or low for primates for their body size? And unfortunately, I don't have the answer for this for you today. This is sort of a watch this space thing. Better question for this conference, though, is, okay, let's say it's true. When did this evolve? Because it can only solve the human adaptive sweet problem if it happened early enough, right, that it can explain these things that show up early in the genus, in the origins of the genus Homo. So here we go back then to, let me take for a second. The problem with evolving a higher metabolic rate, the problem with evolving a higher total energy expenditure is that you put yourself at risk of starvation, okay? This is why not all animals are maxed out on how much energy they can put through a day, right? If energy expenditure is constrained, you can't turn it up, but you also can't turn it down. And so you're stuck with the same energy requirement all the time. And if you evolve a higher one that you can't fund, you're out of luck. You go extinct. Now, some interesting animals and lineages have figured out a way around this. We call it hibernation, right? But primates, other than mouse lemurs, don't hibernate or go through torpor. So we're stuck paying the bills every day. So if you can't pay the bills, you can't evolve a higher metabolic rate. One way of keeping those bills paid, to force the metaphor even further, is by food sharing and also by being fat. And humans do both of those exceptionally well. Humans are the only ape that shares. Other apes don't share food. In fact, we're one of the only mammals that share. And what does sharing do? Sharing means that if I come home empty-handed today, that's okay, because I can share food with you and you'll help me out. Sharing food means little kids that have huge energy demands but don't have the skill sets yet to feed themselves get fed by their parents and by people who aren't their parents. So it's a bet hedging risk against evolving a high metabolic rate. Humans are also the fattest primate by far. We take it for granted that humans, even athletic humans, have body fat percentages in the sort of 15% range. There was just a nice study published by Adrian Zillman and Deb Bolter showing that chimpanzees in zoos being lazy have body fat percentages of less than 5%. So there's something that happened in our evolution that makes complete sense when we put it in the context of evolving a higher metabolic rate, if those data come through. It also gives us something to look for in the fossil record, right? Because metabolisms don't fossilize, but behaviors can. So what can we find? Well, when we go back to this graph and we ask, is there evidence for sharing? When does that happen? The answer is we can all argue and fight, but probably you've got sharing happening as soon as you're eating animals that are too big to eat yourself. And that happens by at least 1.8 million years ago. Here's a nice cut mark on a large bovid from the site of Dmanisi, where Philip gave us the lowdown on the 5 skulls there, about 1.8 million years ago. There's other interesting, tantalizing evidence about adaptations to metabolic changes. Again, changing the diet changes the way you're getting your food. Leslie Aiello also published a seminal paper. The reason that we all talk about her papers has been so important. And this actually doesn't change the importance of that insight, which is that when you get meat eating in the diet, you can get a smaller gut, and that frees up energy for big brains and that kind of thing. We may have also had some change in energy expenditure and efficiency in walking and running, which would again save you some energy and make the energy paradox a little bit easier to figure out. And of course, fire, of course, it comes along pretty late in the game, but cooking and having fire would have also changed our energy budget. And so what I hope I've sparked as you're thinking about this issue of origin of genus Homo and human uniqueness, is that in addition to these fossilized things that we can see very readily, what we have to do is cast a wider net and think about the physiological changes that are happening and include in there a big piece of this story that is metabolic change that allowed us to fuel this human adaptive suite. Thank you.